So you know what's funny is that this is a storage event, but we've talked about everything from storage to compute. And we've talked about networks and throughput, and we've talked about containerization, and we've talked about orchestration. Does anyone find a theme or see a theme there? Anyone? No one? I guess it's a little bit late for that question, but where I'm headed with this is that it's no longer sufficient for us to look at this just from a storage perspective, right? It goes beyond that. It's now we have to look at things in the realm of everything that I just mentioned, right? As an architect myself, it becomes increasingly important to address all of these dimensions of computation and storage, and how do we make them more performant. But it's not just choosing the right components, it's how those components are deployed. And what I'd like to do here is, so before I move on to this, I know there were some questions before about Red Hat and our storage portfolio and our recent acquisition of Ansible. So for those of you who are lucky enough to make it out to Mobile World Congress next month, we will actually be presenting a use case for containerized storage, along with my colleagues back there, Sebastian Hahn and Shmuel Bujna. And I hope I pronounced your name right. Okay. So if you are going to be there, please drop by our booth, and we will have some exciting things to show you. But what I propose to talk about here, and I promised Ross that I would go through this very quickly, is some use cases, and these are use cases that we're seeing emerging, hence the title, but for software-defined storage. Now, traditional storage obviously has its use case, and we understand those workloads very well, but let's all admit to ourselves, right, that for software-defined storage, there are workloads that we simply sometimes still can't get our heads around, right, and we still have to be able to do tremendous amounts of optimization in terms of tuning the software subsystem, but also in terms of selecting the right components so we can get the appropriate results, right, or the desired results. So with that, what I'd like to do is run through some use cases and then just stop for some questions and answers. So the first use case that I'd like to talk about is a historical tick data use case. For those of you that are that have worked in the financial industry, you would be familiar with the term. And then move very quickly into analytics. And I'm sort of building upon the previous solution and how we can put all this together as a sort of a holistic solution for an enterprise. And then also storage for network function virtualization, or NFV, which is another area we're seeing some tremendous scope and opportunity in. And we're working with some of you out there for that. And then also storage for IoT. And as you heard from Kapil previously, and we're seeing a lot of these computation needs move towards the edge of networks, and there are some good reasons for that, which I'll talk about. And then some future use cases, which are based on some of the advents in technology that we've made across the past year. So the things you've already heard about on our roadmaps from Cheyenne, about Gluster, from Sage, which I think, or I hope you found very exciting, with things like the Ceph file system and the things we're going to be doing with the new backing store, etc. So this allows us to now move into new domains that were previously uncharted for software-defined storage. What exactly is a tick? Again, I'm going to just step to this very quickly. Every time you see a security, as the markets open through the day, or the securities market, or the financial markets are open throughout the day, they'll open at 9:30 in the morning, at least on the East Coast and in New York, and then they'll close at 4 o'clock. So throughout the course of a given day, there's all the securities, or as we call it very commonly, stock ticker data that's flowing through these systems. And every time there's a change in that price, no matter how small or large it is, that's a tick. And every time it ticks up is an uptick, and every time it ticks down is a downtick. But behind that, there's this whole there's this whole amount or this amount of data that's being collected, or this vast amount of data that's being collected, which we can leverage to make certain judgments or make certain calls to do certain things with that data. And how we accomplish that is by storing that data, and it's not unlike any other data repository, but today where that data is stored is on very expensive mediums of storage. So with that, if you can move on to the next slide, here's a typical architecture. So for a very simplistic data feed, you'd see the 4 boxes at the far left, which would be basically data feeds. So these are data sources that are feeding the data into what we refer to as market data servers, right? Think of them as these residing at an exchange or residing at a financial firm. And these market data servers basically accept this data. And for the more sophisticated architectures, there's also data sources that feed in from news and social media to aggregate the data, which I'll talk about a little later. And that is ingested into a more real-time database. From that real-time database, once the market closes, there is a historical tick database, which is generated at the end of the day. So as you can see here, this is all the intraday data, which is stored in memory. And then it flows into a historical tick database, which is stored on persistent storage on disk. And this is, as I mentioned, again, stored on very expensive mediums of storage today because it's very, if you can mine this data, it's a very lucrative proposition because you can do things and make certain judgments with this data or calls with this data that were previously, in terms of things like looking at bid-ask spreads and best routes to data or to trades, etc., and how deep a certain trade is, and trade depth and trade breadth, etc. But what we propose with our solution is to be able to store this on software-defined storage, specifically Gluster. So if we move on to the next slide, you'll see an architecture that we propose, which is, again, the same thing that we saw on the previous slide, except now instead of storing it on expensive storage mediums, you have the ability to store it and then subsequently replicate it or geo-replicate it to, and for sort of a high availability environment to another site. And then from here, the sole purpose of this data would be to be mined or extracted, and then you can perform certain, you can run certain mathematical models, or you can run some algorithms against the data to extract some intelligence from that data. So this kind of, as I mentioned, or as I promised, this kind of builds upon the previous slide. So what about that mathematical and that algorithmic data, or those models that we apply to the data? So now we have the data, regardless of where it resides. But what can we actually do with it? So there's yet other use cases for which we can employ the use of software-defined storage. The first one, of course, is we've had a solution that has been published, and you're welcome to look at that. But that's Splunk on Red Hat Cluster Storage. So we have vast amounts of Splunk data, which is collected, and you can actually store that. This architecture has been, we've worked on it in conjunction with Splunk and with some of our customers, and it works very well. And the reason for that is because there's a lot of cold data or less frequently used data which can reside on less expensive storage. The other use case, which is more, if for some of you that are familiar with analytical architectures or big data architectures, as they put it in the industry, there are these new architectures which are referred to as the Lambda architectures and the Kappa architectures. And what those basically mean, I mean, they're fancy terms for basically talking about things like when you have a stream of data, you can do a couple of things with it. So you can do, for those of you that are familiar with Hadoop, you can do a lot of batch analysis with this data, right? And that has its place. But then there's newer types of data which are streaming, from which you need to extract immediate value. There's simply no way you can store the data and be afforded the luxury of keeping it there for analysis at a later time. So things like looking for anomalous events, for looking like, doing things like, if somebody's trying to hack into your system, you're looking for a denial of service attack, you need to be able to understand that immediately, and it's not something that you can go and look at historically. And as you can imagine, as you store this data on batch, as the data comes into your enterprise, you can do things you can have a composite architecture with both batch and real-time analysis, and that is most commonly referred to as your Lambda architecture. However, the compromise you have to make with, or the advantages you get with batch, is that batch can be stored, but it can also take advantage of streaming as well as historical data. The problem with that is you get better results because it's obviously more data, but you compromise because of the time it takes to process that data. With real time, what you really get is you don't really get the quality because you're not getting the sample set or the size of data that you would normally get from batch and analytics, but you get the speed of analysis that you would expect from an analytical architecture. And with that, we move on to yet another architecture, which is the Kappa architecture, which is more of, you can have things like Spark, for those of you who are familiar with the Apache Spark project, and nothing to do with the Spark processor, by the way, but the Spark project, which kind of merges the batch and real-time into a single compute engine or a framework, which allows you to do both batch and real-time analytics in the same engine. And today you can use Red Hat Gluster or software-defined storage to support this framework. So you can store your data, and part of the computation can be done in memory, but when the data sizes need to be, or the data sets need to be stored on disk or read from disk, you can store those for batch. So just to give you a comparison, for the tests that have been run, if you had a traditional Hadoop architecture and you just ran batch using your traditional MapReduce framework on top of that, or computation, Spark in comparison would give you anywhere between 4x to 10x of a speed boost with the same architecture just by employing the Spark engine. And again, this is with the same types of data, with the same data analysis, except now you have to imagine that you're taking, you're building upon some of the deficiencies in MapReduce, and you're taking advantage of Spark, which is now able to load some of the data sets in memory, but you're also taking advantage of a better framework in Spark, which doesn't leverage the exact map, shuffle, and reduce framework of MapReduce. It does it in a different, more efficient way. So with that, I'm just going to move on to the next slide. So again, this is just our Splunk on Red Hat Gluster architecture, where you have some Splunk indexers where the data flows in, and then over time, your data is sort of tiered down natively using Splunk to be stored on Gluster. And again, this is just one of some of the different options in Splunk. You have direct attached storage, you have shared storage, and then you can take advantage of the tiered or the tiering capabilities in Splunk to store the data on a Red Hat Gluster storage framework. So what I really want to talk about here is building upon the first use case, which is now I have all this data and I want to perform some analytics on it. So how would I do that? Well, one way to do it, of course, would be to employ the use of a Hadoop cluster. Another way to do it would be, of course, to take to leverage Spark or Apache Spark, and you can deploy it today as a microservice or a container. And the idea is that you can either have, again, the main difference is you're basically here, in this case, you're leveraging very much like a Hadoop file system, which can be distributed and shared. You can leverage it as a shared file system, or you can leverage it by having individual devices provisioned, or individual sets of data or underlying volumes provisioned to your Spark containers. Now, the difference in figure 1 versus figure 2 is that you have your Red Hat Gluster storage, which is all provisioned down here, and you can scale this elastically and independently, versus here you actually have, as we discussed in the and sort of elaborated upon in the previous Verizon use case, where you can actually deploy Spark and storage containers side by side and have those access storage from this layer down here, which is your compute, or which is your infrastructure layer down here, and it'll all be provisioned and orchestrated, within the realm of an orchestration, whatever that might be, whether it's Mesos or whether or Mesosphere or Kubernetes, and of course there will be there will be a message bus for communication between the architecture. So with that, I'd like to move on to the next slide. So what are some of the key benefits of this architecture? Well, one of the benefits, or as just as we go through them, right, is you have the ability to containerize, again, that theme again of containerization, your Spark computation instances. You have the ability to scale your computation instances elastically, and you have the ability to assign key storage resources, both elastically because they're now confined and isolated. You can now treat them as individual assets, which you can scale independently. And you can pretty much run the same batch analytics, right, with less shuffle. So why wouldn't you do that? And you have now the ability, because of the Kappa architecture, to run both batch and streaming analytics within the same framework. In addition, for some of you that are familiar or that may or may not be familiar, there's also another project called Tachyon. Now, Tachyon essentially allows you to leverage an in-memory file system, which, by the way, or coincidentally, also has the ability to address Gluster FS as a file system underneath, except that you would have Spark compute engines or a Spark framework, as is elaborated in that diagram. You would have Spark compute instances which would perform some of the computation in memory, and as those data sets needed to be persisted, they could be stored on disk, or they could even be stored on Tachyon, which would be another in-memory file system. And as a final tier, it would leverage Gluster FS underneath. So you have many options in terms of defining your tiers of an analytical storage architecture. So with that, I'd like to move on. So storage for network function virtualization. So, just moving beyond and looking beyond network function virtualization, let's think about employing, what if we could do this in containers? Well, at a high level, you have the ability to extend just having virtualization and extend that to, or that architecture lends itself very well to being containerized because of the type of workload that's being deployed within those containers. So I'll give you a very simple example. I by no means am a NFV expert, but again, my specialty is storage. But we have to think about new ideas and new ways of how we can efficiently store data that's spewing from these services running in within the realm of a network infrastructure. So to keep it simple, just look at for example, what a firewall or a load balancer might do. You have the ability to perform a certain service, right? But then you also have that service will also generate some data. Now, what if we had the ability to keep to sort of segregate the service from the data, and you could then virtualize or containerize the actual service, which is essentially what is proposed here and what is being done today, and then store that data separately so that if you did lose the service, it could be scaled as well as reproduced somewhere else in the architecture without any significant impact to the architecture or to the environment. And that is the essence of using or proposing storage or software-defined storage for network function virtualization. So again, as we move on to the next slide, very similar to what we looked at for the previous architecture for Spark, except in this case you have virtual network functions. And again, in the whole scheme of things, the way network function virtualization works is, you typically, just very much like OpenStack or an infrastructure as a service, you've got, something referred to as an NFVI, which is a network function virtualization infrastructure. And that's basically your infrastructure, your storage, your compute, your network, and you need that regardless. But building on top of that, you've got an orchestration, right? And you've got, typically referred to in that space as a MANO or a management network or an infrastructure. But above that, you've got, or that infrastructure, you deploy what are called virtual network functions. Now those virtual network functions, you have the choice of them, or deploying them as virtual machines or VMs, and you also have the choice of containerizing them. And this is what it would look like if they were containerized. Because you now have the ability to have virtual network functions, so things like load balancers and special routing or special switching services. Or in the case of, one of the use cases, or very specific, I'll be a little more specific. If you're trying to design a video streaming workload, and you have, everything that goes from an end-to-end gateway, right from the content provider to a consumer or subscriber of that content, how you would design an entire gateway, an entire workflow in software using virtual network functions. And along each of these points, there's some data generated. And just imagine what we could do, number one, by storing this data more efficiently, because you have to ask yourself the question that how much of this data do we have or would we like to collect, but we are unable to simply because of the cost. Now, if you were able to, or because of cost barriers. Now, if you were able to deploy these as virtual network functions, deploy them entirely as containers, you now have the flexibility and possibly the ability to now store some of that data, not only for the sole purpose of storing it, but also for analyzing that data. So this is what it would look like. And again, very similar to the previous architecture, but another use case. The theme continues. It's very elastic. It's delivered on demand because you can scale these up and down. You can use them for pretty much any workflow that you would have within a network today, because you have the ability to scale them up and down as long as you can segregate the network function from the actual data. You can leverage this architecture. And you can literally deliver this to multi-tenant environments. And this becomes important because if you're trying to deliver this in a true multi-tenant architecture, it's imperative that you deliver also a quality of service. And in some cases, doing that in a shared architecture or doing that, it becomes very difficult. But with these, when you deploy this in the realm of containers, it becomes more deterministic, not only in terms of how you scale, but also when you scale, but also when you need to scale back. And again, there's, we're going to share these slides. We're running a little bit short on time, so I'm going to just skip through these slides a little bit. But the fourth and the last use case proposed here is, again, for IoT and for edge computing. Now, one of the things we're seeing a prominence in is the idea of when you look at a network as a whole, there's the concept of performing a lot of the processing of this data as it's flowing into your enterprise. And that enterprise could be global, for that matter. But doing a lot of this processing at the edge of the network. And the main or the primary driver for that is the ability to reduce or the time to respond, for example, to a customer for quality of service, or for better, for better data, rather than have that come back to your central network to process it and then send it back out with the results. So if you're able to do a lot of this at the edge, in essence what that means is now your edge has to be a little more powerful, or you either that or you have to beef it up, or you have to take advantage of having denser or taking advantage of the same hardware but with increased density. And containers allows you the flexibility of doing that. So if I can draw your attention for a moment, just some predictions, right, from IDC. By 2018, 20% of all IoT intelligent gateways will have container technology, right? And this isn't us. This is just the industry. This is what, this is recorded based on what customers are doing today, right? And then by 2019, 45% of IoT created data will be stored, processed, analyzed, and acted upon close to or at the edge of the network. Right? So these become very important paradigms as we see not only the amount of computation power, but also the amount of, because you need to both process and analyze the data, you need to have, and the acted upon, mind you, the acted upon piece of it could be with intelligent algorithms or intelligent modules that are installed either in hardware or software. But in order to process and analyze that data, you need to store it, right? So it's a problem that has been largely unsolved. And this is the way that we propose to solve it, right, with software-defined storage. In fact, this is pretty much the only way that we can imagine solving it, unless you have a better idea. But, and again, edge computing, just some definitions here, but with that, I'd just like to move on to the next slide. So to give you an idea of the scale of the problem, we've discussed the problem, but to give you an idea of the scale of the problem, again, this is just some IDC data. Just, absorb that for a moment, right? Look at the number of devices, right, by the year 2020, which isn't too far away, by the way. There's going to be about 50 billion connected devices and only 7.6 billion people in the world, right? So that's an average of about 6.5 devices per person, right? And this is a lot larger because there's a lot of people in the underdeveloped world which, who still don't have connected devices or cell phones for that matter, right? So you can imagine that number's probably going to be closer to 8 or 9. And again, just some predictions, right? Within 3 years, 50% of IT networks will transition from having excess capacity to handle additional IoT devices to being network constrained. And why is that? Because right now, the challenge is that all this data is traversing the network to come back to these centralized organizations, rather than have it being processed natively at the edge, right? So it just makes sense to process the data, right, with a better quality of service at the edge. By 2017, 90% of data center and enterprise systems management will rapidly adopt new business models to manage non-traditional infrastructure and bring your own device categories, right? Or bring your own device, bring your own data, however you want to categorize that. The idea is that this is going to result, based on that, in vast amounts of data that need to be stored and vast amounts of data that need to be processed. You also have to remember that for every time that you process data, it generates even more data because there's metadata that's associated with that data. So this is actually a very conservative look. We're talking about problems or data problems or data size problems that of unimaginable, of unimaginable sizes. What we really, what we want to talk about here, or just, again, I want to just get us thinking about this, right? Because it's not about the amount of data that's going to be generated, right? But we have to ask ourselves, how do we come up with new architectures, whether it's in hardware or software, or whatever methodology we choose to employ? How much data do we actually need to store? How much of that data is transient? How much of that data, as I mentioned previously, needs to be stored, but we can't store it today because of cost or capacity constraints? And then within cold storage, so assuming that some of this data is, you sort of formulate the pattern of transient versus non-transient data, and you say, I want to store some of this data. Even within cold storage, what are the access patterns and what are the appropriate mediums? So from the vendors we heard today, right? From Seagate and the different storage mediums, even within cold storage, you'd be surprised to know that there are different patterns of access, right? So in the case of Worm, you just write the data and you never read it again. Or in Archive, you write it once and you never read it again. Or in the case of Worm, where you write it once and you read it many times. Or in the case of, there could be yet another pattern where you write the data, but then you get these infrequent bursts because of, weekly access patterns or whatever it might be, some reporting tool. The idea is that cold storage is no longer just cold storage. You cannot just afford one medium of storage to cold storage and then disregard it. You have to allocate the appropriate, for the best efficiency, the appropriate storage medium to that use case for storage, depending on its temperature. So it's not a capacity issue anymore. We know that we're going to have, a ton of data. It's about enabling the edge nodes, empowering them to filter, index, and compute the data stream. And again, equipping your edge networks with sufficient computation and the appropriate storage combination for both latency sensitive as well as cold or archival storage. Again, some of the key benefits we already talked about, but again, improved quality of service and reduced latency because you don't have to now concern yourself with constraining or bottlenecking the network and building higher throughput networks to transport that data back to your central organization. You can do this at the edge. Higher resiliency because of the broader set of edge components that you will have. And then also, more of a sort of a swarm intelligence because now that your edge nodes are getting smarter and more powerful, you can embed them with smarter technology to deliver data sets or form these redundant pools of storage so they can perform more, whether it's more analytics or different types of intelligence that we haven't even thought of yet. And then, also for higher energy efficiency because you no longer possibly have to deploy components that you need to, or excess components in terms of growing your network or beefing it up. And then because you're leveraging commodity hardware for the most part and open source software implementations. Based on again, the conversations that we had this morning, from everything that you've heard, if you still have questions, please feel free to reach out to us. But again, stay tuned. We're going to see, you're going to see some things about, database workloads on Ceph. We're going to see things about, Ceph-FS, as you heard from Sage, iSCSI, some more hyperconvergent architectures and use cases, more containerization, and support for ARM in newer architectures, so you can take advantage of or leverage the power efficiency over there. And again, this is just this is our last slide, but just in my humble opinion, just some predictions. I don't know how far they're going to go or come true, but again, the increased prevalence and dominance of open source, software-defined storage, containerization, all-flash technologies, for tiering and addressing those needs for latency-sensitive data and analytics. An increased prominence of ARM processors, and then the use of key value drives. For those of you who are not familiar with some of the Ethernet drive technology out there, it's very interesting. It has some very specific use cases. If you have questions, please do let me know.
I think there was a mention of a white paper on the database workloads coming out this week or sometime next week. Can you give more information on that?
It's actually going to be closer. There's still some finessing work that needs to be done, and we need to get some approvals because it's a joint effort. It'll actually be out closer to the end of, to maybe middle of February or closer to the end of February.
I think Brent mentioned earlier about using RAID 0 and the caching on the controller. Is there a downside for that instead of using just bare disk or RAID 0? And is there a pros and cons?
The problem with using RAID 0, you're talking about RAID 0 underneath a Ceph OSD. The problem with that is if you lose a single disk, you lose that entire data set, and so your failure probability goes up by n, however many disks you have.
So Brent also mentioned doing 2 OSDs on 1 NVMe, and I didn't quite understand why you would do that versus just format the whole thing as one OSD.
Yeah, the issue is just that we're currently having trouble generating enough I/O to saturate an NVMe card from a single OSD.
Gotcha.
And so if you just put 2 of them on there, then you're getting more performance out of it.
Right.
Yeah. So I think it's a temporary situation until there's additional performance optimization in the OSD, and then eventually we want to do that.
Thank you.
To continue this point, I wonder if you agree with an idea that says that I'm waiting for Ceph RDMA to break that ceiling, because I believe that the I/O ceiling is bound by the machine and the kernel and the CPUs. Do you agree with that?
Yes. So there's an RDMA effort that Brent probably talked about that Mellanox is spearheading, and it's great. It's not done yet, but it's made good progress. But what they found is that once they sort of eliminate the network bottleneck, they immediately run up against other problems in the I/O stack. So the good news is that there's a whole host of companies, Red Hat included, and Intel, and SanDisk, and Fujitsu, and many others who are focused on solving this problem. So we have a steady stream of optimization patches coming into the tree. So you can expect lots of improvements in Joule. And then we're also working on some more fundamental re-architecting in the OSD to be able to handle some I/O synchronously, some asynchronously, and be able to sort of deal with this situation. So yeah, situation is improving.
So if you have any reference architecture that includes ARM processors and Ceph, ARM processors and Gluster, or?
Yeah, we've done quite a bit of work with the Ceph team directly, actually. And so, as I mentioned earlier, Penguin is one of our partners where we've got single socket 1U system as well as 2U systems. So we've got a couple of different form factor options there. And then we're using latest and greatest Ceph release as well for benchmarking and validation on that. So you'll start to see, I think later this quarter, we're going to be putting out some white papers, Cavium directly. And then we've coordinated with Brent's team over time to make sure the approach we're taking is consistent with the testing that they're doing in their labs. The other thing I mentioned before too is we've got systems in Westford in the Red Hat labs for additional testing and validation too.
Thanks a lot.
I think it's mostly for the Red Hat product management maybe. So I think, I observed, I think both from Cigna and maybe Bloomberg, I guess, kind of, requirement for encryption. Right now they talked about data at rest, and most of the drives do support, right? But they asked for that key management, which is actually the most complex problem of it. Do you have any plans in the works to kind of mitigate the problem, or work with the drive vendors to kind of help you there?
Yeah, so we do support dmcrypt, which is a Linux DM device for both Ceph and Gluster that supports at-rest encryption. The only problem with that is you have to enter a passphrase every time the node reboots, and we don't have a key management solution, which is what you're highlighting. So we do have some ideas and plans which we are working on, so that it's not kind of that tedious to do. On the Gluster side, we actually have a encryption translator, which is more native that we are writing, which will do this. On the Ceph side, do you have a management thing that you do?
Yeah, so the current state on the Ceph side is that the key management is putting everything in etc on the boot disk, which is obviously non-optimal. There's an effort upstream to get a pluggable key management hooks in the startup script so that you can use whatever key manager you use. A long time ago, we built a bunch of stuff into the Ceph monitor, expecting to use that as a key management, but didn't really complete it. So we're hoping to get that in for Joule, but it's sort of unclear whether it's going to make it. So SUSE is interested in this. They have their own key management scheme that they want to use, and we want to have one that's sort of very simple that uses the Ceph monitors. And then there's also a team at Red Hat that's building a new tool called DEO, network-bound encryption, and they have a whole vision about how they want this to work. So we're hoping that we can come up with this sort of pluggable model where we can slot in any one of those three. But I'm moderately confident that it's going to make it in the next month.
I think earlier the duplication was mentioned in Gluster. Is that even possible in Ceph, or does it make sense to have deduplication in Ceph?
Yes and no. You could conceivably do deduplication at the block layer underneath a Ceph OSD, but because of the way that data is distributed in Ceph, you're sort of randomly spraying it across the cluster. The probability that the duplicates of data end up on the same node is low. And so in order for it to really be good, you need to integrate it into the data placement policy. So we have a number of architectural ideas about how to do that, but we haven't really pursued any of them yet. Most likely, we would do it first in the object gateway for the S3 and Swift APIs, because we sort of know the hash up front of the data that you're storing, and we can deduplicate it then. But that's, post-Joule. We're looking at a year or two.
Yeah, no, I think in general we are looking at Linux also for some of these, innovations, because then Ceph and Gluster can use these things as opposed to building them in Ceph and Gluster. So that's one way of looking at it, but that's a long kernel, mainline Linux kernel process. So yeah, there's some thoughts and things like that, but even for Gluster, deduplication would be, as Ceph said, unless you match the replica pair that has the same file that you are trying to put the file on, it may not be. I mean, you kind of have to match up. In Ceph, it's like you stripe, your object across, and then so the possibility of getting a dedupe aware or a dedupe over the chunk or file might decrease when your cluster's size increases. So we have to look into data placement. We have to do intelligent data placement to figure out in which replica pair or which set of OSDs we put in a chunk or a file so that it is actually dedupable. So it's a slightly different problem than a monolithic storage vendor. Yeah.
Okay, well, thank you to all of our speakers.